So we're very happy to have Professor Lam Hui here. He's here to give the theoretical colloquium, but also to attend the workshop is going on gravitational waves theoretical methods. So Lam is a professor at Columbia University. He did, I checked, he did his bachelor at Berkeley, PhD at MIT, and then he did postdoc at Fermilab and the Institute of Advanced Studies, and then through some faculty position, Chicago, he now has been for some years at Columbia. He's very well known for several contributions to the broad field of cosmology. In fact, it's really broad, from analysis of galaxy surveys to theories of modified gravity, even word identities for gravitational fields. Is there an inflation? I think not yet. Not yet. Okay, so that is missing. But otherwise, I mean, not otherwise. So it's very broad and very esteemed. So we're very happy to have him here. Thank you for coming.
Thank you. Thank you, Leonardo. Well, because there's no coffee, so you have excuse to fall asleep if you want to. I don't have that excuse, unfortunately. Just want to check, can we have a show of hands? How many people here are not part of the workshop? I just want to see. They are, okay, great. Thanks for coming, thanks for coming. I'll try to give a nice, gentle introduction. So let me start with, of course, we are in the land of Einstein. A test for you, what are these things? Who is that? You know? And what do you think this is? I guess it's grace, but I cannot interpret exactly what is said here. Somebody please interpret that for me, that would be nice. And what is that? So apparently that's the famous Einstein's log curve, which actually is on this campus. So I was assured by some of the organizers that we'll get to see one of these three things after my talk. So I'll try to finish quickly so that we can go. Here is just a quick acknowledgement of my large number of collaborators. Many of them are here, including Luca, Alessandro, Enrico, and you'll hear from them. But basically, my main two topics, one, the technical summary is here, has to do with tidal deformation. I'll tell you about what that is. And then the second, which has to do with ring down. Again, I'll explain what that is, but they'll focus on what is called quadratic quasi-normal modes. Let me also acknowledge there are a lot of references on what I'm going to talk about. In particular, there are a lot of talks actually that you will hear in the next few days that are on these subjects. And as you heard or just now, in fact, lots of interesting posters. So I'm going to start from the very beginning. I will try to address the question, why do we want to think about black hole perturbation theory? And I'll start with this famous quote from Chandrasekhar. The black holes of nature are the most perfect macroscopic objects there are in the universe. The only elements in their construction are concepts of space and time, which is indeed a true statement. Soon after Einstein wrote down his famous equation, Karl Schwarzschild, not too long after, wrote down the solution, as we know, for a black hole. And we remain fascinated and confounded by all the magical properties of black holes to this day. And they are amazing solutions both because they are simple and profound, right? Simple because they are just solutions of Einstein's equation in vacuum with nothing. There's no matter necessary. It describes how space and time somehow curve upon itself because of the nonlinear nature of gravity and form these objects. And profound because it has so many interesting and magical properties, some of which we will talk about. And let me tell you how we study black holes. We study black holes actually in many ways by perturbing them. So that's why we like to study perturbation theory. It's a time-honored way to study black holes by basically kicking them, throwing objects at them, perturbing them. For example, give you a famous example, Bekenstein. Bekenstein famously started thinking about the thermodynamics of black holes because John Wheeler, his advisor at Princeton, asked him the following question: what happens if you throw a cup of hot tea into the black hole? What happens to the entropy? And that actually led him on the path of formulating the second law of thermodynamics for black holes, formulating the idea of black holes having entropy, that's proportional area and so on. And so it's really a time-honored way to kind of tease out the magical properties of black holes is to actually perturb them. So from a theory point of view, this is a very fruitful way of thinking about black holes. From an observation point of view, is basically black holes, they don't exist in isolation in nature. They always exist in some interesting environments that actually perturb them. And the most dramatic examples is, of course, binary black holes that, in fact, they can merge and produce gravitational waves that we can see, right? And this is, of course, a famous image of black hole. And in fact, the very fact we can take this image is because there is actually stuff around the black holes that are capable of perturbing the black hole. Another question I want to answer before we launch onto the subject is, you might be aware, these days, numerical relativity is very advanced and is capable of just numerically solving the Einstein's equations and telling us a lot about this complicated process such as mergers of black holes. So you might wonder, why do we still want to think about black hole perturbation theory in the old-fashioned paper and pencil way, which is basically what I'm going to focus on? And the answer is that there are situations where there is essentially two different scales and they are widely separated, and it's very hard to solve that system on a computer. For example, if you have a situation where you have a binary and the binary one is very heavy, the other is very light, you have extreme mass ratio, that's very hard to actually solve on a computer. Another example, which is what I'm going to focus on, if you have a black hole and there is a companion, some object far away, the distance between the star and the black hole, let's say, is very large compared to the size, the horizon size of the black hole. In that case, there's also a wide separation of scales, and it's also very hard to solve for the behavior of that system on a computer. And so you have to resort to basically essentially paper and pencil calculations. The very separation of scale, which is challenging for numerical methods, becomes an advantage when you use analytical methods. And that's what I'm going to focus on. And let me also mention the goal. Why are we interested in thinking about these? I would say there are two goals, depending on your point of view. One goal is a lot of us are very interested in testing gravity, testing whether Einstein's his famous equation actually requires corrections. Of course, we are in the land of Einstein, so how dare you think about actually changing the famous equation? The other point of view that you can take is, let's accept that Einstein's equation is really all you need to describe black holes in nature. Then you basically use this system to test for interesting environments about black holes. The simplest assumption that we always made is that the black holes are really Einstein general relativity black holes in vacuum. But in nature, there's always stuff around black holes, including, for example, dark matter. And in fact, for some dark matter models, for axions, for example, you have the right mass, they have the propensity to condense around black holes. In fact, in a way that is actually very significant. And so you could hope to use these methods to, in some sense, probe the existence of interesting things around black holes, including dark matter. So that would be another motivation. So whether you are a fan of Einstein or not, there are interesting things to do, and those are our goals in terms of understanding and interpreting current and future gravitational wave data. In a pragmatic way, let me also add that if you have data that's purely gravitational wave in nature, you do not see any electromagnetic signal. You actually do not have a very, how should I say, you do not actually strictly know whether your object is a neutron star or black hole, especially if they are far apart. They are just point objects. You cannot quite tell which is which. And usually, typically when the gravitational wave collaboration publish their events, typically the interpretation is, well, if the masses are small, less than, let's say, 10 solar mass, a few solar mass or less, typically the assumption is these are probably not black holes and neutron stars, but it's an assumption. Keep in mind there's an assumption, and we want to actually test that assumption. And in fact, what we are going to talk about in terms of tidal deformability, there is a distinct difference between having neutron stars versus black holes, and this is a practical way to tell them apart when you are faced with this gravitational wave data. And so let me now launch onto the subject. I should say black hole perturbation theory is an old subject. It's actually a very old subject. That famous quote was from a textbook by Chandrasekhar in the 80s. So this is something people have worked on for a very long time. There have been some recent advances, and that's what I'm going to tell you about. And they have to do with understanding the hidden symmetries and going beyond linear perturbation theory. So I'm going to start with the subject of tidal deformation. And first, I'll consider what we call linear tidal deformation. So imagine you have, I'm actually going to draw it here. So imagine this is your black hole, and you have a star. The star can be actually another black hole, and it generates a gravitational field that's now experienced by this black hole. But imagine this gravitational field generated by this star has very long wavelength compared to the size of the black hole. So that's the situation we have in mind. Rather analogous to thinking of this as the moon, and this is the Earth, and the tidal field of the moon, as you know, is capable of distorting the ocean's shape around the Earth. And here we are interested in whether this kind of tidal field, what it does to the space-time structure around the black hole. Is there a similar kind of tidal deformation for the black hole? So that's the question. And to quantify it, it's a term that we call love number. So let me explain that to you. In fact, for those of us who don't think about gravity regularly, let me actually start with a simple example, which is electricity and magnetism. Let's say you have a piece of material, some dielectric or some conductor. You apply a constant electric field to it. We all know what happens to that object, right? So the positive charges would tend to accumulate on one side and the negative charges on the other side. And so that creates an induced dipole. So by applying an external electric field, there's going to be an induced response. And the way we describe it in mathematics, you can think of this phi as the electric potential if you want. The external electric field, if you write in terms of the potential, if the electric field is constant, it would go as R to the first power. So that would be L equals 1. But you can also consider more general electric field that has some multiple moments, so expand in spherical harmonics. So in general, it will be R to the L. The fact that you have induced a dipole means far away, you are going to observe an electric potential that goes as 1 over R to the L plus 1. these two solutions are just the familiar ones that we have all seen in our electricity and magnetism class, where you just solve this equation. And as you know, if you expand in spherical harmonics, the two independent solutions are these ones. Yeah, so that's what I'm talking about. And clearly, what I said about electric potential applied to gravitational potential too. You can think about this actually describing the gravitational potential. At least in Newtonian gravity, you have basically the same phenomenon. And so to quantify how tidally deformable your object is, or for electricity and magnetism, how polarizable your material is, you basically look at the solution. This R to the L is the external field, tidal field that you are imposing on your object. And this 1 over R to the L plus 1 tidal tail tells you what is the size of that induced response. And the coefficient that relate them, this lambda, is known as the tidal deformability, or it's called the Love number. Love is the name of a mathematician who came up with this quantity. Or in electricity and magnetism, you would call this polarizability. It goes by different names. I'll just call it the Love number. And the larger this number is, obviously, the more deformable your object is. And to match dimensions for this and this term, this again is the external tidal field. It's basically what this is. And the induced response, if you want, this object actually gets distorted somehow, and it creates a tidal tail. So that tidal tail is this is the R to the L, the tidal tail. That's the induced response. That is the 1 over R to the L plus 1. Okay. And if you match dimensions, this Love number is not dimensionless. It has dimension of some kind of length scale to the 2L plus 1 power. If you just, for this to have the same dimension as that term, you can just read it off. And absent any calculation or measurement even, if you were to naively guess, you would just say, well, given the size of the object, I take it to the 2L plus 1 power. That would be your 0 order guess for the Love number. Yeah. And therefore, if you were to do it for a black hole, that's what your guess would be too. So if you do not do any calculation, you would say, well, the horizon size to the 2L plus 1 power is probably the Love number for the black hole. Interestingly, for a long time, it's known that the Love number for black hole is in fact 0, exactly 0. And I say exact, I should put some caveats. Here I'm talking about a tidal field that is constant in time, that does not vary in time. And the situation you should keep in mind is something like this. Again, think about the Earth and the Moon now. Of course, the tidal field for the Moon actually changes with time because the Moon moves around, but it moves around so slowly that moment by moment, if you want to figure out the tide, the actual tidal response of the ocean, you can just pretend the tidal field from the Moon is just static, moment by moment. That would be actually a very good approximation. You can forget about the monthly motion of the Moon around the Earth. So that's the static limit that I'm taking. And it turns out for static tidal field, it has been known for a long time that the Love number is 0. And my task, I hope, in the next maybe 15 minutes is to show you why is it 0. First of all, let me explain to you how do people actually do that calculation. And then I'll try to explain to you what is the magic behind. So the way the calculation done is actually very simple. You do black hole perturbation theory. And so this is my attempt to explain to you how that works without giving you the details. So you take Einstein's equation and you say the metric, what I call G here, I skip all the indices. So this is the metric. You say is equal to the metric of a Schwarzschild or a curved black hole, let's say, plus small perturbations. And the small perturbation, I'm going to use the symbol phi. Think of this phi as basically the analog of this phi up there, okay? But it has indices which I'm skipping. So think of this phi as small perturbations around a background, which is a Schwarzschild or Kerr black hole that we know and love. You take this and plug into Einstein's equation, and you linearize, and you keep all the linear terms in the small perturbation, and you will schematically arrive at an equation of this form. It is second order in derivatives, and it has some kind of potential. The existence of the potential is because your black hole background is not flat, it's non-trivial. And so you have some kind of potential. Just to give you a sense of what that potential looks like, if you plot that potential as a function of distance from the black hole, it looks something like this. So in this kind of drawing, the peak of that potential is roughly 3½ times the size of the black hole. So it's not at the horizon, it's a little bit outside the horizon. That peak is often called the light ring. And this potential vanishes as you go towards the horizon, and it vanishes as you go far away. It's a potential that looks like that, okay? And for a Schwarzschild black hole, that potential goes by the name of Reggie-Wheeler potential. And it has long been known that black hole has vanishing love numbers, and this calculation has been done by many, many people. Schwarzschild, Kerr, Reisner-Nordstrom, and so on. And how do they conclude that the love number is 0? It's in fact very easy. It's a very simple argument. It goes as follows. You have an equation that is second order, which means there are always 2 independent solutions. And then you ask yourself, how do these 2 independent solutions behave close to the horizon and far away, okay? Let's talk about far away first. When you're very far away from the black hole, you are basically back to what I'm showing you here. You just forget about the fact that your space is actually curved. And the solution is what I told you. R to the L and 1 over R to the L plus 1. In general, your solution should be a linear superposition of these 2 independent behavior at large distance. So that's familiar. That requires no explanation. It turns out, and this is something I'm just going to claim, it's actually not too hard to show. But if you take this equation and you analyze it close to the horizon, what I call RS here is the Schwarzschild radius. That's where the horizon is. It turns out the 2 independent solutions have the following behavior. One, a possibility is equal to a constant, some kind of number at the horizon, finite constant. The other possibility is a log, and you can see this log diverges at the horizon. As the radius approach RS, the Schwarzschild radius, this actually is logarithmically divergent. So these are the 2 asymptotic behaviors, one far away and one close to the horizon. And it's something is actually not hard at all by just looking at this equation and deduce, okay? Now, where does the vanishing of the love number come from? It comes from basically this. First, you say, well, if this variable is something that we can physically measure somehow, if it's an observable, and for this, you have to be a little bit careful. You probably do not want to just look at the metric perturbation in some random gauge. You have to be careful and look at the right quantities. But assume you do all that, and this is the right quantity that is observable. You probably want to forbid an observable quantity that is actually divergent at the horizon. Because we believe the horizon around a black hole should not be a special place. You should be able to have well-defined measurable quantities. If you fall into the horizon, nothing actually very bad would happen. And so generally, we would say, let me cross that out. Let me say, my solution, whatever that is, the physical solution, should not have this log behavior. And so you cross that out. And it turns out now, if you actually solve this equation, you look at your exact solutions and you impose this regularity at the horizon. It turns out, and it's not actually hard to show that either, that Far away, turns out this is absent. This 1 over r to the L plus 1 tail is absent. And this is what I call the love number surprise. What is the surprise? The surprise is the following, that by demanding regularity of horizon, one would think generically, if I put some condition on the far left, on the far right, generically, it should still be a superposition of these two things. How come? No. For the black hole, it turns out one of this behavior is gone. Yeah? So that's what I would call the love number surprise. I'm just going to pause here in case there are questions. Please do interrupt me as we go along. So this is the love number surprise. So this behavior has been known for a long time. The fact that once you impose a regularity far away, instead of having a generic mixture of these two behaviors, this tidal tail is gone, is what led all these people and others to conclude this lambda, whatever that number is, for a black hole is actually 0. Yeah, the love number is 0. The tidal deformability defined as such is 0. And the way I phrase it, I hope at least it makes sense to you that this seems to be a bit of a surprise. It's not a generic behavior. In fact, if you do this calculation for a star, let's say, and you impose boundary conditions at the surface of the star, you would conclude, you will find the generic behavior. You will find that far away, you have indeed a generic mixture of both, which tells you the star has non-zero love number. So having non-zero love number should be a generic behavior. Having 0 should be a surprise, and somehow it demands an explanation. So that's what I'm going to tell you now. What is the explanation, our understanding of it? Does that make sense? I want to reinforce for you the idea that this demands explanation. So I'm going to give you another example. The example is this one. This is forget about black hole for a second. Let's do quantum mechanics. And quantum mechanics in 1 dimension. This is a potential. And let's send in some wave that scatter off this potential, right? So usually, let's say I send in this wave. Going to the left, let me call it e to the I kx. After encountering this potential, there would be a transmitted wave going in the same direction. And generically, you expect a reflected wave going in this direction. Now, that would be a textbook examples of some scattering problem, quantum mechanical scattering problem for some potential. Generically, this is what you find, no? The analog of the vanishing love number is the following, is to say there is some potential that is so special that by demanding this wave is left going on the far left, on the far right, this is absent. And in quantum mechanics, if you encounter a potential like this, you would be a bit surprised. This is a potential that has no reflection, pure transmission. And you will want to know, okay, what is so special about that potential? So essentially, we are asking the same question for the vanishing of love number for black hole. Yeah, Laura. This is static, 0 frequency. Yeah. Yeah, so when you have a non-zero frequency, in fact, the 2 branches should be ingoing, outgoing mode, as you know. And usually we would demand ingoing into the horizon as your boundary condition. And you will see, in fact, if you look at it in the right regime, in R, you will see there would be the analog of this tidal tail is actually there for non-zero frequency. So this, what I'm telling you, is a special property of 0 frequency. Yeah. Thanks for asking. Are there other questions before I move on and try to tell you, okay, what is behind this surprise? What is the magic? Okay, very good. Please do stop me. I don't need to finish the talk. We can all go look at one of those three things. Okay, good. To tell you that story, it requires a little bit of work. We have to do some work, so I hope you'll bear with me. The main two ingredients, which are kind of, in some sense, reason ingredients, is some kind of symmetry understanding of the vanishing of the love number. But before that, it's actually also important that we have a good definition of love number. I think for that part, I think I will be relatively brief because I also already tell you the definition here in this way, but for the purists, they could be they could challenge me. How is this love number? Is it completely well defined? Could whether it vanish or not depend on exactly which variable I look at? There will be those kinds of questions. So let me just very briefly answer that question first. And it has to do with what we call using a world-line effective field theory of description of basically a generic object that interact with gravity. So roughly speaking, your action has the usual Einstein-Hilbert action that comes from general relativity. You have a particle. This is the world line of that particle. Imagine you're an observer very, very far away from your object of interest, which might or might not be a black hole. This is the world line of the object. So in your action, you would have a world line term that is just given by the mass of that object times integrated over the proper time of that world line. And it turns out you can show, and I'm just going to claim it here, there are operators you can write down that are localized on the world line that describe and code finite size effects. The fact that even though you're very far away, this object is actually not a true point. It has some finite size, and therefore potentially tidally deformable. And this term has a coefficient which is precisely the love number. So it's basically this kind of definitions that we use to more properly define what the love number is. But you can, if this part is too much for you, you can just forget about this part. Just look at my definition in the previous slide. That would be good enough for us. So the next part is where I actually really try to explain to you the magic. So bear with me. This is going to be a very busy slide. I'm actually trying to explain you the magic in one slide. So I'm going to use this slide and keep adding things to it. Okay. So before we do that, let me tell you, at first, try to answer this question seems pretty hopeless because the equations, the famous equation that describes small perturbations around a curved black hole looks very complicated. And I'm not even to explain to you all those symbols. This is the Kerr metric. This is what is called the Tarkovsky equation. It looks like a mess. So how do we even figure out why this magic happens? And so here's what I propose we do. We do something simple first, and then we try to build on those lessons. So to understand the love number surprise, let's think about a simple system first, which is basically a massless scalar, which again I call phi, is going to be the proxy for the gravitational perturbation I talked about earlier. A massless scalar living in the Schwarzschild background, this is the Schwarzschild metric. The main thing that you want to pay attention to is this symbol, which I call delta here. This is a function of radius, and it vanishes at the horizon. When the radius is at the Schwarzschild radius, it vanishes. That's the main important thing. And you can write down precisely what this equation is. You just basically need to remember when you contract derivatives here, you have to use the metric, which is given here. And remember, we are setting time derivative to 0. We are looking at static tidal response. And we are going to follow what we usually do in the electricity and magnetism. We would expand in spherical harmonics. And once you do all that, it turns out this equation becomes this equation. Now this looks more manageable. No, this doesn't look that complicated. Surely we can understand what is going on behind this equation. Why the love number surprise, okay? But even staring at this, actually you'll be scratching your head, what's going on? And so you want to make it even simpler. And to make it even simpler, let's look at the special case where L is just 0, no? Then cannot be simpler than that, no? So let's do that. So for L equals 0, the equation of motion now has the following form, and I try to write in a suggestive way. There is these D minus and plus, I'm going to call them lowering and raising operators, kind of like simple harmonic oscillator. It turns out when you set L equals 0, you have basically only this term, and you can think of delta dr as the lowering operator, and you can think of dr as the raising operator. And the equation of motion for L equals 0 take this simple form. And then you recall what you actually do in quantum mechanics for a simple harmonic oscillator. You say, well, to figure out the ground state, you basically demand that the ground state solution is annihilated by the lowering operator. No, that's what you usually do. And it turns out that logic works. It works here perfectly. And why is that useful? It's useful because this equation now is a first order equation. Yes, the ground state does not have this confusion between, oh, I have two independent solutions, why is one absent? That's no longer there because this is now a first order equation that tells you how the ground state behaves. And so it directly connects one behavior with the horizon. There's only one possible behavior at the horizon with only one possible behavior far away. And in the case of L equals 0, it's so simple, you can just solve it. Clearly, this equation is solved by basically the monopole. L equals 0 is just a constant. It's a constant everywhere, clearly regular at the horizon, and far away. It corresponds to R to the 0, and no 1 over R to the L plus 1, so no tidal tail. So this is precisely the solution that connects regularity at the horizon with purely growing rather than decaying behavior far away. That's it. That's for L equals 0 is so simple. That's the behavior. And what is amazing is that this logic works for higher L. So more generally, if you give me any L, this equation of motion can always be understood to be in this form, where there is a raising and lowering operators. There's some constant that is L dependent. And it turns out the L dependence is such that there is a ground state at L equals 0, so this constant vanishes, which is what you see in this example. And what is interesting is that this raising and lowering operator has this funny property. It actually is really raising and lowering in the sense of raising and lowering L. It turns out you can check. It takes a solution at level L and take it to a solution at L plus 1 or minus 1, depending on which operator you use. So really the phrase as such, the analogy with simple harmonic oscillator is actually complete. It's really the same as harmonic oscillator, except think of the usual excited levels as the analog of L here. So L equals 0 is the ground state. And then if you act successively with raising operator, you would reach basically non-zero L. Does that make sense? And it turns out the fact that this is the regular solution that have no love number at the ground state, and you stare at basically the form of the raising operators. For higher L, it's actually more complicated than this, but not much more complicated. You can convince yourself for all the non-zero L, the same is true. Regular at the horizon means no tidal tail far away for all of them. You can just immediately see And so this turns out to be the reason, using this simple harmonic oscillator analogy. But for those of you, for those of us who are like, really want to know what is behind all these, again, if you want, let me rephrase the surprise. The surprise is actually the existence of this raising and lowering structure itself. Why is it there? And it turns out there is actually a deep reason why they have to be there. And here's almost the end of my very busy slide. It turns out, where do they come from? They come from the following. If you think about, again, this equation, which is where we started from, with time derivative set to 0, it turns out it's the same as thinking about your scalar as living effectively in some kind of three-dimensional space. And it's basically this one. It doesn't look too different from the spatial part of the Schwarzschild metric. It's conformal to it. And it turns out this space has magical properties. And the magical properties are the following. This space is obviously spherically symmetric. So we have 3 killing vectors. J are the generators of rotation, X, Y, and Z. Yeah. But it turns out it has 3 more symmetries. And these symmetries come from actually conformal killing vectors of this space. In fact, this space has 7 conformal killing vectors, but only 3 of them obey this very special condition that the divergence is harmonic. And it turns out this condition allows you to conclude a scalar that lives in that space, even though it's not conformally coupled, has symmetry generated by these 3 conformal killing vectors. It's really a special condition obeyed by these 3 conformal killing vectors. So these 3J and 3K are the 6 symmetries obeyed by this scalar. And if you want, if you ask me to put a finger on what is the surprise, I would say this is the surprise. That somehow this equation with time derivative set to 0, not only does it has SO3 rotational symmetry, but it has 3 more. Those are the not obvious ones. And if you check the symmetry algebra, this J and K, they form an algebra that actually looks like Lorentz, SO31. And to just, in case you are curious, what is this symmetry transformation on the scalar? It looks like this. It looks very unfamiliar, probably to you. But if you express this in Cartesian coordinates and take the large R limit, these are actually just special conformal transformation at large R. That's what they are. And finally, just one more line on my full slide. So what does this SO31 have to do with existence of this ladder structure? And it's basically the following. If you organize your solutions by spherical harmonics labeled by L and M, they form a non-trivial representation of this group SO31. In technical terms, it's called a principal series representation. And what does that mean? Well, for J, it's very simple. We know we are familiar with the fact that rotation, some of the rotation at least, they raise and lower M, no? So Jx plus or minus Ijy, they raise and lower M. And it turns out you can show these K, they raise and lower L, basically. That's what they do. And therefore, this completes my story. So let me say it again. So the fact that you have this scalar, massless scalar, living in your Schwarzschild background, surprisingly has SO31 symmetry. And following from that, there are operators, symmetry operators that actually raise and lower L, from which this whole ladder structure follows. And then this ground state argument basically get around this confusion about having 2 independent solutions and why you only have one of them, because you have reduced the problem to first order. So that's it. That's the explanation. I'm going to pause here after this very long explanations. So this is all my explanation in one slide. I hope it makes sense. It makes sense to you.
Can I ask you, in this picture,
please.
what happens if I send RS to 0? So why are black holes special? I see that the minus now vanishes in the origin rather than horizon. I cannot see immediately why this is peculiar to black holes.
Why? You mean sending RS to 0?
RS to 0.
If you send RS to 0, actually what happens is this symmetry algebra, actually, if you remember, special conformal, the conformal group, the conformal transformations, K and K, they actually commute. Yeah. So whereas here, actually K and J, if K and K actually give you J, and actually it's because there is a factor of RS that you are actually using to actually have that algebra. So it's a good question, but the fact that you actually have this algebra is because RS is actually non-zero. You can check if you just recall what you know about the flat space conformal group and reduce yourself to just rotation and special conformal transformation. It does not have this algebra. Yeah. Are there other questions? Okay, very good. How much time am I? Almost there. 15 minutes. Okay, let me make some additional comments beyond what I just told you. So I just told you basically the simplest possible case, which is a spin 0 perturbation, which is just a scalar minimally coupled to gravity in a black hole background. And for that, the love number is 0. It turns out this reasoning can be applied to spin 1 and 2 perturbations around Schwarzschild black hole. You just have to do a bit extra hard work to find the right variables. If you find the right variable, choose the right gauge and all that, you will find the same story repeated for both the parity even, the electric part, and the parity odd, the magnetic part of the tidal deformation. It works for both electricity magnetism spin 1 and also for spin 2 perturbations. As long as you choose the right variables. So I'm not going to go into detail of that. This SO31 symmetry can be used to, if you like the well-lined way of thinking about love number, you can explain why they are 0 by basically invoking this symmetry in the large distance limit. In case you are interested, you're wondering about Kerr, how about Kerr? Because everything I told you apply to Schwarzschild. For Kerr, it turns out of those 3 conformal transformations, K, X, Y, and Z, the one along Z, the spin axis of the black hole survives. That one is the hidden symmetry for Kerr. And representation theory using that actually tells you you have a ladder structure also, and so you can repeat the same argument for spin 0. And then to get to spin 1 and 2, turns out there is a separate ladder that raise and lower spin. And then you can apply that to the Tokowski equation to complete the argument of also for Kerr. So it works. More complicated for Kerr, but it works. Let me make a comment about higher dimensional black holes. In case you are wondering, the same actually structure exists for arbitrary dimensions. This constant here turns out to have L dependence, just like the 4-dimensional case, except the L dependence always comes through this combination, which I call L hat here, which is L divided by D minus 3. For D equals 4, which is what we have been focusing on, L hat is just the same as L, but in general, they are different. And it turns out to run the ground state argument, you want this constant to be 0 at the ground state, which actually corresponds to L hat equals 0. And then these ladder operators just increment L hat by integers. So by that argument, it tells you that in arbitrary dimensions, the love number should actually only vanish for integer L hat, which is actually the correct pattern as verified by explicit calculations. So this kind of ladder reasoning works for higher dimensions. Recently, with Luca and Oscar and others who are here, we also are able to extend some of these symmetry reasoning to axis symmetric perturbations, but nonlinear, going beyond linear theory around Schwarzschild black hole. And using essentially similar reasoning, you can show a subset of all the nonlinear love numbers are also 0. Yeah. And you should pay attention to a talk by Alexandro, who has a different way of thinking about it that can actually show all the love numbers are zero, beyond what we are able to argue here. So I think this concludes the love number part of my talk, which is probably most of my talk. Any questions? Yeah, Alexandra. Yeah. Running, I'm not sure we have too much to say, because you really have to think about going beyond linear. You really have to think about nonlinear things. And because we are really focusing on linear things, we don't have too much to say. But maybe these we have, but this work, we only focus on 4 dimensions. Yeah, it's a good question. Other questions? Okay, so let me briefly tell you about ring down. No, this is the picture you have in mind. This is actually real data. When you have 2 black holes going around each other, you emit gravitational waves, and the waveform, the signal as a function of time, looks something like this. Oscillate as the black hole get closer and closer together. At some point they merge, and the merger is right around here. After they merge, you have a bigger black hole that initially is very perturbed, and it executes oscillations that have distinctive harmonics that eventually die down. And so this phase is what we call ring down. So it's like a bell that actually has harmonics, and those harmonics have definite frequencies, which tell us a lot about the space-time structure around the black hole. That's why we are interested in them. And usually the way we think about this is, again, doing perturbation theory. So this is the same schematic equation that I showed you earlier. This, if you want, would be the linear equation where you drop all quadratic and higher terms in the Einstein equation, assuming phi, the perturbation is small, the linear equation. And if you solve that linear equation, you would find these harmonics with the right boundary conditions and so on. Schematically, if you actually keep second order terms, you should probably find an equation that looks like this. In addition to the linear terms, which are grouped to the left with some potential, there are also terms that are quadratic in the perturbations, and I move them to the right. So this would be schematically what you should expect. And the way you would solve these equations beyond linear perturbation theory is to do the usual expansion. You say your perturbation is composed of first order perturbation plus second order and so on. Second order is of the order of the first order square. And the linear rise equation basically tells you this is true. And then if you plug in the second order, this must be true. So this operator operating on the second order perturbation must be sourced by the first order perturbation square. So that's a very, I'm not doing anything fancy. These are all very simple reasoning. But once you arrive at that reasoning, you immediately, almost without doing any work, have some predictions for what you should see. Because if phi 1 has one of these harmonics, which, for example, I take the dominant harmonic, which is a 2-2-0 mode, which is L equals 2, M equals 2, and overtone equals 0, that's a fundamental mode. That frequency, if that is the time dependence of the first order perturbation, you plug it on the right-hand side, you square it, it must source a second order mode that is twice that frequency. No, just a sum of the linear quasi-normal mode. And clearly this reasoning I can apply to any pair of harmonics. And so just this very simple reasoning alone tells you that if you look at perturbations when they are large, especially when you are close to the merger phase, where these second order perturbations are non-negligible, you should expect actually a richer spectrum. And that richer spectrum, without doing any work, should just be a sum of pair of the linear spectrum. It's a very simple reasoning. And recently, we did a check, basically tried to measure this, detect this in numerical simulations. And there was a separate group based at Hopkins that did the same. Let me show you the results. The result is actually plotted here. So what am I showing you here? So here's what we do. So take these numerical simulations of mergers of two black holes. And each of these points correspond to one of those simulations where you vary the mass ratio, you vary the spin, and so on. And for each of them, we are able to identify the omega 220 mode, that's the linear quasi-normal mode. And we are able to identify a mode that is actually twice the frequency, so that's the second order quasi-normal mode. And we plot the amplitude of one versus the other. The x-axis is the amplitude of the linear 220. The y-axis in the upper panel is the amplitude of the quadratic quasi-normal mode. If the story I'm telling you is correct, you should expect generically this amplitude should scale as this amplitude square. And to guide your eye, we drew basically this to show you, look, it has the right behavior, just to guide your eye. But let me also emphasize, if I plot other quantities, I would not have this behavior. For example, if I plot the linear 440 versus linear 220, it looks like this. It's not actually this kind of behavior. So it's check like this that convince ourselves that, yes, we probably have seen the quadratic quasi-normal modes in numerical simulations. And the fact that we can see in numerical simulations suggests when the data gets good enough, we'll see in the real world, in real data. And I think that would be very exciting because I think it will give us new ways to test general relativity or test for interesting environments around black holes. And I think because I'm running out of time, I'm going to skip what I wanted to say about the Green's function. You might remember Laura gave a nice description of that, so I'm going to skip all that. I'll just tell you why we are interested in this. The last bullet point, why should we care? First of all, if you go beyond linear perturbation theory, you might hope that you can have a better modeling of the ring down because they are there anyway. These modes are there. It's just a matter of whether you can see them. And maybe by keeping track of higher order perturbation, you can actually make good use of the data closer to merger time, where you have higher signal to noise. And perhaps for me, most interestingly, the amplitude of the second quasi-normal mode divided by the first, the linear quasi-normal mode square, that ratio tells you something about the nonlinear structure of the perturbations around a black hole. And that is something that is predicted by Einstein's equations. And amplitude is usually the thing that we do not focus on when we look at ring down data. Usually we focus on the harmonics. But this kind of argument tells you that, in fact, there's information about the amplitudes that actually allows you to actually use it and test for general relativity. And I think Enrico might be talking about that, I assume, yes. so go listen to his talk. And I think I'm going to wrap up here. So I told you, I hope I'm able to convey to you why love numbers of black holes in 4 dimensions asymptotically flat, they actually vanish. And if you forget everything I said, basically think about lattice structure that arise from SO31. That's the basic message. In terms of kind of follow-up questions, you might wonder, I mean, if anything, the main message, the main lesson I learned is that somehow black holes are smarter than us, at least smarter than me. Somehow they have these magical symmetries that we didn't realize before. Could there be more? And I think already there are some hints that there are probably more. I can tell you, if you are interested, that might actually even work for dynamical perturbations. Already we know there are some approximate symmetries for low frequency perturbations. Can they help explain the quasi-normal spectrum? Can they help us predict and understand dynamical tidal response? You might also want to go in a different direction. You know, think about neutron stars. Maybe neutron stars are objects that are sufficiently close to being a black hole, where these symmetries are somehow weakly broken. And if they are weakly broken, maybe that will help explain certain universal relations people have found about neutron stars that relate different quantities about neutron stars, is quadrupole moment, is tidal deformability, and so on, maybe. For nonlinear ring down, again, what I wanted to emphasize, these higher order quasi-normal modes, they have to be there, just by simple reasoning. And probably one of our challenge is to somehow disentangle the quasi-normal spectrum from initial conditions, which is something that Laura talks about in her talk already. And to end, let me go back to here. Thank you.
Thank you, Lam, for this beautiful talk. We have time for questions.
So yeah, so for the quasi-normal mode for the nonlinear regime, the thing we talked about at the end, for the magnitude, is there some idea how to see this experimentally? Because it might be very difficult, I guess.
Yeah, certainly not with current data. We have done our own error forecast, and there are other groups that also have. With future data, it should be possible, at least for the lower lying quadratic quasi-normal modes, not with current data. Yeah. I think it's probably what people call 3G or something like that, not 2G. Yeah, yeah.
I think in one of your slides, you showed that you can, in numerical simulations at least, you can measure the quadratic mode even at relatively late times.
Yes.
After the peak.
Yes.
So do you think that it would be affected by the kind of time dependence of the source or the time dependence of the initial data, or would it be more?
I think it would be. I think it would be. And in fact, that's why we start at that part is we start at 15M, no? It's because of basically our worries about that. And it seems to me, in order for the field to make progress to use this as tests of general relativity, we must actually understand better the kind of the time dependence that come from the initial conditions, like what you were stressing. Yeah.
Mm-hmm.
Thanks for a nice talk, Lam. About these ladder operators and connections to quasi-normal modes, besides going to neutron stars, does it help to go to simpler objects like boson stars where you have complete control over the system? And has it been calculated? Like how these, because they must be.
People have computed tidal deformability of boson stars, maybe even somebody here in the audience. People have, yes.
But do the mathematical structures that we have, right, does it approach a black hole in a systematic way? Because there you can keep on changing the compactness up to some critical value.
So what happens is in any of these given objects, what actually, let's take a strictly symmetric star. Outside, you have all the same basically Schwarzschild metric and so on. And so it would appear all these ladder symmetries, they are there. What actually breaks is actually the boundary condition at the surface of the star. And nobody has really studied carefully how it breaks precisely in this kind of language. I think it would be a good thing to do, to quantify in what sense you have weak breaking of these things from the boundary condition. That would be nice, yeah. Although keep in mind, as long as you impose certain energy condition, there seems to be some gap between the most compact star and a black hole. So it's not like you can go there continuously unless you're willing to violate some energy condition. Yeah.
So this SO 3,1 symmetry smells like the hydrogen atom or the Kepler problem and the Runge-Length vector. Is this the same physics behind it, or is it different?
It's tempting. So the for the hydrogen atom, the key is basically this this extra Runge vector.
Yes.
And in the end, it generates a phase-space symmetry, which doesn't seem to be these extra symmetries. These extra symmetries are not like that. The extra symmetries of the hydrogen atom, they are more like in general relativity having killing tensor. They are more like that kind of symmetries, some kind of phase-space symmetries. So I agree, it's very tempting to relate them, but they seem to be a little bit different as far as we know. Yeah, thanks for asking.
Another last question? If not, let's thank Lam again.
Thank you. Are we going to see one of these? You understand that? Okay. Okay.